onto the Moodle. So therefore, today, if you have any questions, certainly you can look back from the video, and also you can give me an email such that I can answer you, right? And because the we need some make-up lecture. Otherwise, we may not be able to go through all the tutorial problems that I planned for you. So therefore, would you please put down the 30th of this month, the last day of this month. So this Wednesday, so it's 6:30 to 9:30. So there will be our makeup class. 6:30 to 9:30. So there will be the first makeup class, and I think we need at least 2 to 3 makeup classes of this subject, in order such that we can teach a little bit slowly. I want to do it slowly, such that to give you enough time for you to ask questions, and also I can give you a more explanation on all the lecture notes, right? So therefore, would you please put that mark down on your diary? I have already also put into the calendar that the makeup class, the last day of this month, 6:30 to 9:30. Okay. And also, some students asked me about the group size of the project, of the air conditioning project. Okay. So I will accept a group of 2 students or 3 students. So you can form your own group, either 2 to 3 students. No more than 3. So don't tell me that, well, we are 4 students, can we form a group? In that case, you break down yourself into two student groups. Okay? So 2 or 3. And if you insist on your work on yourself, I don't mind. If you say, I work on myself, therefore I am a one-man band. Okay. Then you want to do more, then it's up to you, right? Okay. So care about the group size, right? Right. So in that case, let us make a start. So now, let us start again with the concept of thermodynamic process. So now in front of you, can you see the PowerPoint presentation? 你睇到嘅係咪個 PowerPoint 啊？係咪？係。Okay, thank you. So therefore, let us assuming that we have some working fluid, let's say air. Now, the air is keeping at the initial pressure P1 and the initial volume of V1, right? So assuming that P1 is a low pressure, for example, atmospheric, right? And V1 is a very big volume, So therefore, we put this air into the piston and cylinder combination of the compressor. We call this starting point stage one, right? So therefore, what I need to do, I want to apply a work done, and then applying the work done and compress and push the piston inward. Therefore, to compress the air from a low pressure P1 to a high pressure P2. So initially it's keeping at P1, V1, and then after compression, I will compress the air to a high pressure P2, but in the case, the volume is reduced to a very small volume V2. Now, change from stage 1 to stage 2, this duration is called a process. 整個過程就係叫一個 process. And during this process, what I have applied into the working fluid is the work energy. So I transfer the work energy through the piston and into the air. Because of this work energy input, I'm able to increase the pressure from P1 to P2, right? So therefore, the work done, the work energy transfer, is the energy transfer during the process. Work energy 同埋 heat energy 呢兩樣嘢咧，都係喺個過程裏邊睇到嘅。嗱，當佢喺1嘅時候，喺 stage 1嘅時候，呢個 air 所有擁有嘅嗰個 properties 咧係冇 work 嘅嚇，佢嘅 energy 係 internal energy。咁但係喺整個過程裏邊咧，我哋加呢個 energy 落去咧，就以 work 嘅形式加落去。咁咧，我哋就 transfer 咗呢個 work energy 俾入去呢個 air 樹啦。所以咧，由之後咧喺呢個 process 之後咧，個 air 嘅含有嘅 internal energy 就高咗咯噃。咁喺邊度表現到出嚟咧？就係佢個 pressure 係高咗好多，係表現到出嚟啦。因為一個 high pressure 嘅 fluid 咧，係佢嘅 energy level 係高好多嘅。咁所以 work 同埋 heat 咧，要記住，都係喺個過程裏邊 transfer 入去或者 transfer 出嚟嘅嗰個 energy 嘅 amount 或者 rate。所以 work 同 heat 都係喺嗰個過程裏邊涉及到嘅嗰個 energy transfer。Therefore, clearly we specify that work and heat, yes, they are energy. They are energy. However, they are the form of energy during the transfer between 1 and 2. Okay? And also work and heat are the energy can be transferred across the boundary. Now, in front of you is a non-flow process, a non-flow system. We are assuming that the air will be kept inside the system throughout. Therefore, working fluid will not be allowed to go out or to go in. This is a typical non-flow process. But work can be transferred through the piston into the cylinder. So therefore, it can be transferred across the boundary, crossing the boundary, just like heat. Heat can also be transferred across the boundary. But as heat work and heat are the energy transferred during the process. Therefore, how many work has been transferred? How many heat have been transferred? is very much directly depending on the process itself, how to carry out the process. Example, from 1 to 2, if this process involves low loss, that is a very ideal compression process, then the work we input in relatively will be less when compared to between the two stages, a very high loss is encountered. Then because we need to apply additional work to overcome the loss, not just to compress it from low pressure to high pressure, but also overcome the losses. In that case, we need to provide a much higher work. So therefore, how many work will be involved between two end states, 1 and 2, is very much depending on the actual process. This is an important concept. So if I compress air from P1 to P2, how many work I need to play is not a constant value. It's not a constant value. How many work I need to provide will be highly depending on how the process is carrying out. Okay? Okay? Now, I mentioned back to just the diagram we have. So we are compressing air from low pressure big volume to high pressure small volume. So in that case, at stage 1, pressure is low, volume is big. At stage 2, pressure is high and volume is small. In other words, during this process, 1 is the starting point, 2 is the ending point. And we can observe that change in both pressure and volume. In order to show the change in both pressure and volume, then it is more convenient to put pressure and volume onto the same graph, a plot. And we call this plot the property diagram. And this property diagram making use of pressure as the y-axis and volume as the x-axis. So therefore, we can also call this property diagram a PV diagram. P is pressure, V is volume. On a PV diagram, a plot, a dot here, for example, point 1, then already gives you the reading of the pressure and also the reading of the volume. Point 2, also a single point, also gives you the pressure and the volume. So therefore, from point 1 to point 2, it is very clear that we can observe the change in both pressure and volume. This is the why we use property diagram. Now, if we are changing from point 1 to point 2, in between, the changes in between, how the change is carrying out, is known as the process. I can show the process by a line. So from point 1 to point 2, if following this solid line, then it's very clear that you can see how the pressure is changing, how the volume is changing. But why I can represent the process by two kinds of lines? One is solid line and one is dotted line. Because solid line showing that the process between state 1 and state 2 is an ideal process. Ideal 理想化嘅 low loss. There is no loss. Therefore, an ideal process representing that there is no loss. And because there is no loss, therefore we believe this process can be reversed back. So we can apply work and then compress it to high pressure. Taking out the work, then it can be reversed back to the original point. Because there is no loss, we can do it. So therefore, an ideal process referring to a process have no loss. And we call this kind of process a reversible process. However, in actual case, then loss is always encountered. We always have loss, right? So therefore, if always have loss, that means this actual process cannot be reversed back because you keep on losing something to the surrounding and disappear. You cannot get all this loss back. Therefore, an actual process always have loss. And we call the actual process a irreversible process. That means it cannot be reversed back. And to represent a irreversible process, we always use a dotted line. Now, in actual practice, almost we never have an ideal reversible process. All kind of process will encounter loss, high or low, still have loss. So therefore, actual process always have loss, and we always meet the actual process. Irreversible process, ideal process, too good to be true. 點會冇 loss 㗎？係咪啊？所以真實嘅 process 咧係唔會 reversible 嘅。But in doing our analysis, we usually assuming that the thermodynamic process are reversible, even though we know that it's not true. However, we assume that they are reversible. Why? If it is not reversible, it will be very difficult for us to analyze. 如果唔係reversible 咧，好難分析嘅。咁所以咧，唯有 assume 佢 reversible 咯。So therefore, bear in mind, actual process always have loss. But in doing the analysis, we usually assume it to be ideal, to be reversible. Otherwise, you will have great difficulty to analyze them. Okay? In order to change the properties from state 1 to state 2, what we need is usually energy transfer. And energy transfer only in two kinds, either heat or work. So, let's talk a little bit more about heat and work. In thermodynamics, usually you will see that both heat and work can be positive or negative. And sometimes we use a Q to represent heat, but sometimes we put a small dot on the top of Q. Why? So let me explain. positive and negative are directions. If we apply a work from the surrounding into the system, just like this diagram, we apply a work through the piston that is from the surrounding into the system, from the surrounding into the system. Now this kind of work is negative. We call this direction negative. From surrounding into the system is negative. However, if the work is produced by the system back to the surrounding, such as we have a diesel engine, so the diesel engine produces a work to the surrounding, that is from the system to the surrounding, that is positive work. However, heat is exactly opposite. So from the surrounding into the system, we call it positive heat. If work is negative work, if heat is positive heat. However, if the heat is rejecting from the system back to the surrounding, then it is a negative heat. We always say that the heat is rejecting back to us, therefore it is negative. So therefore, both positive and negative referring to directions. And if we are saying that now let's input a certain amount of energy into the system, say heat, okay, we input a certain amount of heat energy into the system, amount, kilogram, then we can represent this amount using kilo, a certain amount. For example, now we input 100 kilojoule of heat energy into the system. Then this 100 kilojoule is the amount. Then we use simply Q. But if we said no, now we are inputting 100 kilojoule per second of heat into the system per second. That is, we relate to the time. That is amount per second. In that case, we put a small dot onto the Q. This small dot here means per second. So if the amount is kilojoule, put a small dot on that is kilojoule per second. What is kilojoule per second? Someone tell me, what is kilojoule per second? Can someone tell me, what is that? Kilojoule per second, what is that? What do we call? Come on. 2 marks question.
Rate of heat.
Yeah, kilojoule per second, how do we call? Kilowatt, right? Kilowatt. And then if we talk about work, then if we said, let us put 100 kilojoule of work energy into this system, then again, we're talking about a certain amount. Then if this is work, then we use a W to represent it. However, if we said no, we're talking about 100 kilojoule per second, then we will put down a small dot on the top of W. The small dot here also means that per second. Kilojoule per second is kilowatt. Work per second, we give it another name. What is that? Work per second. What is that? Power. So therefore, heat, amount of heat, we call it heat. The rate of heat transfer, also heat. There's no other names. But for work, amount of work is work. Work per second, that is the rate of work, we call power. Okay? Okay? So now, let us show a summary. The two energy that transfer during a process will be either heat or work. So we usually use Q to represent heat. Put a dot onto that, then it's the heat, amount of heat per second. That is, we link it up with time per second. Work, we use W to represent that. Put a dot onto the W, then it's a rate of work. Work per second, then we also call it power. Now, heat and work are all the energy transferred during the process. Therefore, they are not properties of the system. We only have 6 properties of the system. We are usually used: pressure, time, volume, internal energy, enthalpy, and entropy. Heat and work, no, they are not properties, right? They are the energy that can be transferred across the boundary during a process. Heat is driven by a temperature difference. So if we have a temperature difference, then it becomes a driving force to drive the heat energy to flow from high temperature to low temperature. Work, that is the force times the displacement. Now, work, we got to have something move. A displacement is a movement. So therefore, if you do not have a movement, then you do not have work. Question here? Any question here? If not, then let us go a little bit further into the process. The process, I have already explained the process. In thermodynamics, we have 2 kinds of systems: the non-flow and the flow. When the working fluid is not allowed to flow in or flow out of the system, then it is a non-flow system. Sometimes we call it a closed system. Non-flow, low flow, right? But if we allow the working fluid to flow in and then flow out, then the working fluid can be allowed to cross the boundary to out or in. Then we call this a flow system. A flow system. Sometimes we also call it an open system. Then in order to describe what happened inside the process undergoing in the non-flow system, then we call this process a non-flow process. The process undergoing inside a non-flow system that we call a non-flow process. To describe what happened inside a non-flow process, especially about the heat transfer, the work transfer, and also the change in properties, that we rely on so-called the non-flow equation. In a flow system, then when a flow system is going through a process, then we call this process a flow process. And the equation used to describe what happened inside a flow process, that is the steady flow energy equation. Non-flow equation applied to a non-flow system. Steady flow energy equation applying to a flow system. Right? So now, let us go into these two kinds. First, I will talk about the non-flow first. So when a non-flow system, we can call it a closed system, goes through a process, then it is a non-flow process. And the equation to describe this non-flow process is what we call the non-flow equation. Now, let us go back to the diagram. This is a typical non-flow system because the air will not be allowed to cross the boundary. So therefore, the inside the air cannot go out, and outside the air also cannot go in. So therefore, it is a typical non-flow system. The non-flow system starting with state 1, that is P1 and V1, and then of course T1, U1, H1, and then by supplying a work done to compress it, then it will become a high pressure air at the end of the process, right? So therefore, at the end of the process, all the properties change, may change. Pressure change from P1 to P2, volume change from V1 to V2, temperature change from T1 to T2, and the internal energy may also change from U1 to U2. Who caused this change? This work done. Do we have heat as well? I don't know. May have heat transfer also. In a process, we can always apply either heat or work or both. So at the same time, we can apply heat, and we can also apply work at the same time. And then once we have that, the system can be changed. Right. So therefore, how to relate the work done during the process, the heat transfer during the process, and also the properties at the beginning and the properties at the end of this process. How to relate them together using the non-flow equation. This equation tells you that in a non-flow process, we can apply heat 1 to 2, that is throughout the process from 1 to 2. We may also have work output or input, the work done from 1 to 2 throughout the whole process. So if there is difference between them, then these difference in energy, they are also energy. So don't forget, they are also energy. If there's any difference in this energy, these two energies, then this energy will either be going to the fluid to increase the internal energy from U1 to U2, or take away from the fluid such that the energy will be decreased from U1 to U2, depending on which one is bigger, right? So therefore, M is the total mass inside the system. So if we have 10 kilograms of air inside the system, the mass is 10 kilograms. So this is the law and flow equation. Heat during 1 to 2, the process, minus the work done during 1 to 2 of the process, equal to the mass, total mass, times the internal energy change. A very simple energy statement gives you the law and flow energy equation. Remember this equation. So remember this equation, right? So now, if we have a process, talking about the process as shown before, so we start from P1, V1, and T1, air. And then input a work to compress it, and it become P2, V2, and T2. So therefore, what I want always ask is how many work I need to apply. And because of this work applied, for example, what is the final pressure? What is the final temperature? Right? So these are all the questions I want to ask. And all these questions can be solved by using the law and flow equation. However, look at this equation, very simple equation, but it is not easy to solve. It is not easy to solve. Why? Too many unknowns. Here, normally I know what is the starting point. So therefore, I know what is the starting point at point 1. The pressure, the volume, the temperature, the internal energy, and so on. But in order to work out how much heat are input, how many work are provided, there are two unknowns already. And even worse, then usually what is the internal energy, for example, at the end of the process, U2. Sometimes it is also an unknown. So therefore, 3 unknowns may be in one equation. How to solve? So therefore, the equation itself is simple. However, how to solve it is difficult because involving too many unknowns. Now, in order to tackle a law and flow system, then there's no doubt this law and flow energy equation will be the starting point. No doubt. And then how to get the answer, solve the answer known, such that we can solve the equation completely. How? So now, let us work on that one by one. First, in more fluid properties, here we have fluid properties U1 and U2. That is the internal energy. Now, last lecture, I already teach you how to solve, how to read out the properties of a working fluid. And there are two main kinds of working fluid we have. One is known as the perfect gas. This kind of working fluid always remain as gas. Therefore, we can solve this kind of working fluid, the perfect gas, with some linear equation, such as PV equal RT, U equal CV times T, H equal CP times T. I ask you to remember that. So therefore, knowing how to solve the properties of a working fluid usually will help us to deal with this side. For example, if we are working on a steam, water and steam, then U1 and U2 normally can be found from the steam table. However, if the working fluid that we are looking at are gas, then we are using linear simple equations. For a gas, U internal energy is equal to CV times T. So therefore, this side can be rewritten into MCV bracket T2 minus T1. But in that case, the temperature T must be absolute temperature because we are dealing with a gas. So therefore, if we can measure T1 and T2, can we measure temperature? Yes, we can measure temperature. So therefore, if we can measure T1 and T2, then this side solve, right? Up to this point, any question? Any question? Any question? I'm waiting for your response, please. You got to tell me even though you have no questions, right? Otherwise, I simply do not know whether I should proceed or whether I should give you more explanation, right? 冇人講嘢。
冇問題啊，Sir。
Okay, now that's it. So what I really want to have is your response. Otherwise, how do I know that whether you understand my teaching or not? So therefore, on the right hand side, then we can base on the methods that we are finding the fluid properties. Repeat again. You got to know what kind of fluid that you are dealing with. Gas or liquid and vapor, right? Clearly, You need to know. You need to know. Okay, then on the left-hand side, we still have two. We still have two unknowns: heat and work. And both heat and work are dependent on the process. Depending on process. So therefore, we need to know more about what kind of process that we are dealing with. Now in thermodynamics, we have sorry, a while. Wait. Yes. Hi.可唔可以遲啲至俾？我而家上堂，因為你聽朝俾電話我，你聽朝俾電話我。OK， 好，拜拜。Sorry about that. So therefore, in thermodynamics, we have model several processes based on their characteristics. So therefore, we will look at what is the special characteristics of a certain process, and then we try to build up an ideal model for this particular process. 嗱，以後我想講嘅呢啲 process 咧，其實都係一啲理想化咗嘅一啲 models 嚟嘅啫。但係咧，因為咁樣咧，可以幫到我哋手去計算個 process 本身啦。Therefore, let us talk about several kinds of process. In other words, several models, right? The first kind I'll talk about is a constant volume process. Now, very simple. If I have a can, let's say, of water. So I put water into a can. But this will not move. So all the walls are rigid. So the can have a fixed volume, and all the walls are rigid. So therefore, if all the walls are rigid, then we will say that there will be no change in the volume. There will be no change in the volume. So therefore, when we put this can, let's say, of water to heat it up, then what we are doing is to let it go through a constant volume heating process. So we simply produce heat to bring the temperature up, right? But throughout the whole process, from 1 to 2, volume remain unchanged. So therefore, it is purely a constant volume heating process or cooling. Okay. Then, how to solve? First, the work done of this kind of process. We normally start from the work done, because we have another very simple equation to solve the work done of a non-flow system, non-flow process. 嗱，呢條 equation 咧，一定只係能夠用喺 non-flow, right? For non-flow process from 1 to 2, for example, we heat up from state 1 to state 2, so the work during this, throughout this process, is W1 to 2. W is work. 1 to 2 is from point 1 to point 2. Can be given by this simple equation. Integral of P dV from 1 to 2. P is pressure. V is volume. dV, a small change in volume. A small change in volume. So we can solve this integral of P dV from 1 to 2 to work out how much work. But for a constant volume process, volume remains unchanged. Therefore, there is no change in volume. dV, a small change in volume, but there's no more change. No change. So therefore, dV is 0. dV is 0. No change in volume. So we multiply P with 0. Gives you 0. Integrate from 1 to 2 of 0. Give you 0. So therefore, for a constant volume process, 0 work. We can prove it using the Newton's second law. Newton's second law saying that work equal to force times displacement. But now we do not have any displacement because there's no movement, no change in volume, therefore there's no displacement, 0 displacement. Force times 0 displacement gives you 0 work. So therefore, no matter you're using 1 to 2, integral of 1 to 2 of P dV, or using the Newton's second law, both give you the same thing. That is, for constant volume process, no work. We go back to the law and flow equation, cross out the work. There's no work. Therefore, the heat we introduce into the system from 1 to 2 is simply equal to the mass times the internal energy change from U1 to U2. If this inside the fluid is a gas, then it's simple, because U can be rewritten into CV times T. So therefore, this side becomes mCV T2 minus T1. In other words, if we know T1, if we know T2, then we can work out heat transfer. Okay? So we start from the law and flow equation. And then first tackle the work, the law and flow work. And for a constant volume process, this work equals 0. So therefore, substitute back into the law and flow equation. The heat transfer simply equal to the mass times the internal energy change. So if this is steam, then you need to find out U1 and U2 directly from the table. If this is a gas, then you change U1 and U2 into CV times T1 and T2. Then if you can work out T1 and T2, then you solve also the heat. 0 work, and then we have heat, and heat can be solved like that. Now, if the other side is a steam, then you can base on the steam table to work out U1 and U2, therefore solve. But if it is a perfect gas, then what we need is to change U1 and U2 into CV T2 minus T1. And if you can solve out T1 and T2, again, solve. However, usually T1 is a low value. We will know T1 easily. but in some case, T2 may not be so easy to measure. Therefore, in this kind of calculation, normally we will have some problem to find out what is T2. If this is the case, then let me show you how to do that. Now, if a non-flow, remember non-flow, a constant volume process, the working fluid is a gas, then we cannot look at the table, we cannot apply them. Then remember, this kind of process, non-flow, constant volume process, working fluid is a gas, then we always have two equations to help us. Remember, we always have two equations to help us. First equation comes from the process itself. What is the characteristics of this process? Now this process is constant volume process. So therefore the characteristics is volume equal constant. Right? Simple. Constant volume, therefore volume equal constant. Now this is the first equation. First equation comes from the process itself. Second equation, it is a gas. Therefore, second equation is the gas law. Second equation, the gas law, that is always PV over T is a constant value. Now, this is a gas. Therefore, PV over T is a constant value. This is the second equation. Now, I substitute the first equation into the second. PV over T is constant. V is also a constant. So therefore, P over T is also a constant, right? P over T is constant, then you can rewrite into P1 over T1 equal P2 over T2. I can further rearrange. So it gives you P2 over P1 equal to T2 over T1. In other words, the volume rate, the temperature ratio is the pressure ratio. So if we know P1, we know P2, we know T1, and therefore we can work out T2. It is how we can work out the properties if this is a gas. If this is a steam, then we go back to the steam table. Okay, so up to this point, any problem? Up to this point, any problem?
No problem.
Good. So even though your classmate said that he has no problem, but if you have problem, you can also always you can voice it out, right? Okay, so this is the first kind, a very simple process. So in this process, volume equal constant, and the pressure ratio equal to the temperature ratio, work done equals 0, heat transfer equal to the mCV T2 minus T1, right? Everything solved. Everything solved. Second kind, we put a working fluid inside a cylinder trapped by a piston. But this piston is allowed to move. So what we are doing is to input a heat up the working fluid. If we heat up the working fluid, what happened? The working fluid expand. Working fluid expand. It expand and then drive the piston out from here to here. Drive it out from here to here. Now, it's always acting on a constant pressure acting on the piston. So outside it is a certain pressure, so we always have a constant pressure acting upon the piston. So therefore, this time we are not keeping the volume constant, but we are keeping the pressure constant. The pressure will be constant at a certain value. Now, this is what we call the non-flow constant pressure process. Non-flow, we are also starting with the non-flow equation. Q12 minus W12 equal M times U2 minus U1, right? So therefore, I have already changed it. Why it haven't been changed? Okay, wait for a moment, because I have already revised this PowerPoint today, so I used a new one. Give me 2 minutes. Give me 2 minutes. I surprise, because I have already done that this morning. I don't know why it come back to the same old PowerPoint.等我一陣下，因為今日我改過呢個 PowerPoint 嚟嘅。我好奇怪點解仲未改咧咁。Yes, OK， 好啦，我用翻呢個落去得啦。Sorry to keep you waiting for a while, because I want to use the new PowerPoint that I have prepared just today. Okay. 好。大家而家係咪睇到個 PowerPoint 啊？
係啊。
係咪 ？OK。Then I'm talking about this non-flow constant pressure process. Notice that this time we supply a heat to heat up the fluid inside. Therefore, it expand and then drive the piston out. Drive the piston out, right? So therefore, the volume is expanding from V1 to V2. So V1 is this one. V2 is this one. So the volume is expanding. However, the pressure is keeping constant throughout. So therefore, we also apply the law and flow equation. Law and flow equation, Q12 minus W12 equal M times U2 minus U1. Again, first, you need to know what kind of working fluid that you are dealing with. If this is, say, water and steam, then on the other side, this internal energy U1 and U2 should be solved by steam table. However, if this is perfect gas, then we should solve this unknown, these properties, by using those equations. Okay? Okay. And then now, in this law and flow equation, the first one we will tackle is the work. Work. So work equal integral of PdV from 1 to 2. Now, in the last process, the constant volume process, there's no change in volume, therefore dV is 0. So therefore, basically we do not need to solve because everything is 0. But this time, no. Volume is changing. We have work. So therefore, we need to solve this integral. We need to solve this integral of PdV, right, from 1 to 2. How to solve an integral of PdV? Then remember, there are two cases that you can solve this integral. First, pressure is a constant. 2, pressure can be rewritten in terms of V. In other words, it's a function of V. So either one that you can solve this integral. This time, the pressure is a constant. Therefore, we can solve this integral by taking the P outside. Taking the P outside the integral. It is constant, so therefore you can take it outside the integral. So it becomes P times integral of dV from 1 to 2. Now, integration of dV is very simple. Simple integration. Integral of dV is V. So therefore, we change it into the integral of dV become V, just V. Lower limit is 1, upper limit is 2. So become like that, right? If dV become V, so we simply substitute 1 and 2 into that, so become V2 minus V1. So therefore, integral from 1 to 2 of dV become V2 minus V1. And then we can simply multiply the pressure back because it is a constant value. So therefore, for a constant pressure process, the work become pressure times the volume change, V2 minus V1. We can also rewrite the total volume big V into mass times specific volume small v. So M times small v2 equal big V2. M times small v1 equal big v1. So therefore, work done can be the total mass times the pressure times the specific volume at 2 minus specific volume at 1. So therefore, it is the work done. Right? Once we solve the work done, then we can substitute this work back into the law and flow equation. Substitute this work in the law and flow equation. So it becomes the heat from 1 to 2 equal to mass times U2 minus U1 plus mass times P2V2 minus P1V1. Why P equal P2 and equal P1? Because they are constant value. P equal P2 equal P1 and equal to a constant value, because this is a constant pressure process. However, we may group this together because U2 plus P2V2 is the definition of enthalpy, H. U plus PV is H. So therefore, U2 plus P2V2 is H2. U1 plus P1V1 is H1. So, in a constant pressure process, work is M times P times small v2 minus small v1. And heat is the mass times, now this time not internal energy, but it's enthalpy, H2 minus H1. So if the working fluid is a water and steam, then what you need is to, from the steam table, to work out what is V1, what is V2, what is H1, what is H2, and you solve both heat and work. However, if it is a perfect gas, then how to change PV? Using PV equal RT, gas law. So therefore, PV2 equal RT2. And PV1 equal RT1. For H, H for gas can be divided into Cp times T. Not Cv, Cp times T. But this time, the temperature T got to be absolute temperature. Right? Also, for a constant pressure process, we can also apply the two equations if the working fluid is a gas to further help us. The first equation comes from the process, the constant pressure process. Therefore, pressure is a constant, right? The second equation is always PV over T is a constant because it is a gas. Combine these two, PV over T equal constant, P equal constant, therefore V over T is also a constant. We may further rewrite into V1 over T1 equal V2 over T2. This can also be further rewritten to temperature ratio T2 over T1 is exactly equal to the volume ratio, V2 over V1. So therefore, if we know the volume change, we can also predict the temperature change. Problem? Problem? Problem. If not, then let me talk about the last process. This is what we call the non-flow adiabatic process. This kind of process, we normally call it is a process related to work done only. Because the word adiabatic means that Q equal 0, low heat transfer. We also call this kind of process isentropic process. Isentropic. Isen, constant. Tropic, entropy. So this is also known as a constant entropy process. I will explain it later on when we come to the steam power plant. Then I will further explain how we use this kind of a constant entropy, how to make use of these properties, entropy. But once you see this process, no matter you see isentropic or we write as a reversible adiabatic, then they're the same, because reversible plus adiabatic exactly equal to isentropic. Okay? Once we look at that, then very simple. This is non-flow process. Therefore, we can use the non-flow equation. And this time a little bit different, because we notice that this is adiabatic. Adiabatic means low heat transfer. So without any calculation, we have no need to do any calculation. We can simply say that Q equals 0 already. So therefore, it's not necessary to do any calculation at all. If this is 0, then the work done is simply equal to the mass times the change of internal energy. But this time is U1 minus U2, not U2 minus U1. Why? Because before the W should have a negative sign. So therefore, we absorb the negative sign to the other side. Instead of U2 minus U1, we have U1 minus U2. Okay? So if this is steam, then from the table, we work out U1 and U2. Gives you the work done. But if this is a gas, then U1 and U2 can be changed into CV T1 minus T2. And in other words, what we need is to find out T1 and T2. Now, again, we always have the two equations helping you to find the relation between the pressure ratio and the temperature ratio and the volume ratio. Always remember these two equations. First equation comes from the process. This time. If it is a constant volume, then volume equal constant. Constant pressure, pressure equal constant. But what is the process characteristics of an isentropic process? Remember that it is pressure volume to the power gamma, pressure times volume to the power gamma is a constant. That means pressure change, volume change. There's no constant volume or no constant pressure. Both pressure and volume are changing. But the pressure times the volume to the power gamma, it will give you a constant value. That is P1 V1 to the power gamma equal P2 V2 to the power gamma. Up. What is gamma? What is gamma? Right? What is gamma?俾個答到我有2分加。It's the ratio between Cp over Cv. Gamma is the ratio between the two specific heats, Cp over Cv. This gamma is a constant value for a certain gas. Air, if this is air, then gamma is always 1.4. If the fluid is air, then gamma is 1.4, right? Remember, gamma is Cp over Cv. And what is Cp minus Cv? 咁有冇人答到個 CP 減 CV 係乜嘢啊？乜嘢
Hello.
Very good. Give me your name. 你叫咩名？我真係加你2分㗎，你講啦。嗱，1、2。
梁文康。
嚇？
梁文康。
Okay. I remember you. 嚇？記住你㗎。如果你需要呢2分去 upgrade 嘅，或者需要合格嘅，我即刻俾你，無條件，因為我記得你答咗呢個問題。Very good, very good. Now, for isentropic process or a adiabatic process, going through by a perfect gas. 嗱。當我 working for a perfect gas 嘅時候，至好用呢個關係噃。PV gamma equal constant 係個 gas 至可以用㗎。點解咧？因為 gamma 係 gas 嚟㗎，係 gas 嘅 CP 同 gas 嘅 CV 嘅 ratio 嚇。Steam 係冇呢樣嘢㗎，所以呢個咧係當我isentropic process 如果 working for a perfect gas 嘅時候先至好用。OK? OK? Therefore, process characteristics PV gamma equal constant. Second equation always work. Always work. Because it is a perfect gas, so therefore the second equation comes from the gas law. PV over T equal constant. 永遠記得有呢2條 equation 係幫到你㗎，永遠。如果係一個 non-flow process， 如果 working for 係 gas， 咁呢2條 equation 就永遠幫到你㗎。第一條會變嘅 ，depends on 個 process 係乜嘢。第二條係不變嘅，因為呢個 P over T 等於 constant 係 apply to 嗰個 gas 㗎嘛，所以係不變嘅。OK。Therefore, from equation 1, we can rewrite PV gamma equal constant into P1 V1 to the power gamma equal P2 V2 to the power gamma. Rearrange. It gives you equation 4. That is P2 over P1 equal to V1 over V2 bracket the whole ratio to the power gamma. 嗱，呢個好有用㗎。我哋買部 diesel engine 翻嚟，咁咧佢嘅運作係已經定好晒㗎啦，即係個 V1 係幾大 ，V2 係幾大，定晒㗎，唔到你喐㗎啦。因為呢個係涉及到嗰個 engine 嘅衝程嚟㗎嘛。fix 咗 V1 同 V2， 佢淨講俾你聽㗎。哦 ，V1 over V2， 譬如話係10啦咁。咁呢個定咗㗎啦，但係咧，即係話呢個係 given value 嚟㗎。Based on 呢個 given value， 咁好容易啦。V1 over V2 係等於10喎，咁咪10條 power gamma 咯。如果嗰個 gas 嘅 gamma 假設係 1.4， 咁咪10條 power 1.4咯。一撳計數機已經撳到啦。而呢個就等於個 pressure 嘅 ratio。咁如果你知道 P1， 你咪可以計到 P2 咯。straightforward， 係咪啊？係咪？咁所以喺呢度咧，知道個 volume ratio 咧就好簡單，好多時都俾你㗎。嗰個 manufacturer 會俾你㗎。咁你知道呢個 volume ratio 咧，好容易俾你計到個 pressure 啦。咁我唔係想知個 pressure， 我想知個 temperature 噃。咁啊點咧？一樣得。嗱 ，equation 1 PV gamma equal constant。equation 2 PV over T 等於 constant。and then we divide equation 1 by equation 2。1比2除，個 T 上咗上邊啦，個 P cancel 咗啦。個 V 咧係 V to power gamma 除以 V to power 1，即係 V to power gamma minus 1。Therefore, dividing 1 by 2, it gives you T times V to power gamma minus 1 equal constant. And we can rewrite it into T1 V1 to the power gamma minus 1 equal T2 V2 to the power gamma minus 1. From equation 3, we can rewrite into 5. Therefore, temperature ratio T2 minus T1 equal to, again, the volume ratio V1 over V2, the whole bracket to the power gamma minus 1. 咁如果呢個 V1 over V2 係知嘅，譬如假設係10咁啊，加埋 1.4， 1.4減1咪 0.4 咯，咁即係話係10 to the power 0.4， 又係一撳機就得啦。咁咧，你知道 T1 就好容易 work out T2 啦。嗱，喺呢度咧，我哋俾到晒你就係 pressure 同 volume 之間嘅關係 ，temperature 同 volume 之間嘅關係。咁如果我想知道 pressure 同 temperature 之間又有冇關係咧？咁好簡單啫，我將 equation 4 substitute 落去5裏邊，因為 equation 4咧你可以改寫成 V1 over V2 等於 P2 over P1 whole bracket to the power 1 over gamma to the power 1 over gamma， 我將 gamma 調咗過對面，咁然後將呢個 V1 over V2 substitute 翻落嚟5呢度，咁於是乎咧你就可以得到 temperature ratio T over T1 等於 pressure ratio P over P1 to the power gamma minus 1 over gamma 啦。咁於是乎咧，呢兩條 start from 呢兩條 equation， 我俾到你嘅係 pressure 嘅 ratio with volume ratio， temperature ratio with volume ratio，and then temperature ratio with pressure ratio， 齊晒。咁咧 乜嘢嘅數你都可以 solve 得到啦。OK， 好啦，咁我哋停5分鐘，好嗎？咁咧，我哋係喺5:05開始翻啦。好 ，take a break 啦。OK。Go。 辛苦你。他今年是第3年去了，过去2年都是3.5分。所以今年3.5不一定明年就一定可以，不一定的。我们这里有好几个同事都是3.5分，3.5分，个3年下来也是3.5分。如果是这个的就是很困难的，你有一个突破，如果没有的，就是拿不到钱了。现在，在他们看来，这个 topics 没有什么 innovation，有时候他们就很困难给你钱的了。因为还有就是那个 panel 呢，不简单的。我看过那个 engineering 那个 panel 来讲，那个很强的。其中一个是那个从前是我们 PolyUMG 的那个 head of department，现在他去了那个 CTU， 他现在是副校长啊。他的那个research很强。如果他一看你没有什么，他觉得你没有什么特别的，你就很困难拿钱。所以为什么今年这个 Ivy 拿不到，他的 project 拿不到，我还没看那个 comment。可能因为去年我拿了一个了。他今年跟我的那个有一点
相似，对
了，所以如果有这个样子，
所以他也不会给，因为他觉得有人做过，
已经有了。
对，这点我知道。以前我们写 proposal 的时候，都要去看最近这几年有没有别人做过，然后就不能再做类似的，不然他不愿意给你这个钱。
对了，他们常都希望。为什么他们比较喜欢呢？将那个给一些比较年轻的新的也不一定是他们是因为那个GRF 呢，就是他们8大购否的那一个人，他们有一个特别的那个钱的是
给那个新的人，我知道
新的就是 ECS early career scheme。不过我觉得我们在这一边的时候，这个基本上没有的，是没有。不过还有比较新的人呢，就是有一个好处，是因为你比较年轻了，你那个想的东西，一般来讲都比较新一点，老的很多时间做下来还不容易把这个抛掉，很困难的。你在这个 topic 里边呢，文章也发表过很多篇了，你很困难把今年不做了，我重新再做另外一些，困难的。所以这个也不，这个有时不容易玩。
其实挺难的，因为我以前也给温老师写 proposal 嘛，其实有时候很多的时候你要想，他们想要什么样子的，然后再看一下别人没有做的，然后还要想有新的 idea， 这3个加在一起就非常困难的，其实是非常困难的。你还要吸引那些 panel， 你觉得我觉得你这个很不错，但是统一来讲，我们组用这种 UAV 方向就很好拿。然后那种 AI 和 machine learning 这种就是政府会比较喜欢的。
对了，不过也有它的困难了。
对，
在这个方面很多人做。
对，很多人做。
现在
我们
都是的， 这个课题比较新，
对，
拿前辈好像比较容易，一窝蜂的去做，
对，都一窝蜂。然后就上次就觉得有一个我们组就是无人 UAV 的和那个就是 BSE 好像是 BSE 的合作了一个 project，是用无人机在海滩捡垃圾。我们觉得怎么可能有这样的 proposal， 然后就写出来，结果就中了，就拿到奖。
很难讲啊，
很难讲，真的很难讲。
很难讲啊，因为我觉得差不多一般来讲都是这个运势。
对，有的时候运气也是对。
这个是真的，
唉，没办法，这种事情。
我们这里的 office 就是office 不够用，真的不过也好的，如果你明年来了，非常有可能呢，你要跟这个 Maggie， 去 share 一个房间了。我们这里有一些房间比较大，是2个人的。现在他做在这里边15楼，在15楼上边，刚好咯。因为我们也有看到一男一女的，我们不能够放在同一个房间，因为真的有不方便。对，
不方便确实。
对。OK。哎 ，Go。Hello。大家翻嚟未
？Hello。
Okay. Then let us make. Hello. Make a start. Okay. I want to start this section 2. This next section with example. All right. So therefore, we go to the class tutorial. That is the example. So I want to do some problem solving for you. Right. So now let us go to the question 3. So are you looking at the question 3? So air. Now, when we look at a question, several things we need to determine. Very important. First, is it a flow system or a non-flow system? This is the first thing you need to determine. So air at 1 bar and 25 degrees centigrade is compressed to 6 bar atypically and reversibly in a cylinder of an air compressor. So this is inside the cylinder of an air compressor. So therefore, there's no doubt this is a non-flow system. Right? So the first thing, tell yourself it is a non-flow or it is a flow. Right? Secondly, what kind of working fluid it is. We only have 2 kinds, either gas or liquid and vapor. And liquid and vapor is normally water and steam. So when we read the question, the first word already tell you that air. So therefore, no doubt, it is a perfect gas. So therefore, we have a perfect gas going through a non-flow process. What kind of process it is? adiabatic process. So therefore, it is a process having P times V to the power gamma equal constant. And then, what are the given data? Given data, first, air at 1 bar. Now, if the working fluid is a gas, I will advise you the pressure better keep it in kilopascal, kPa. And how to change 1 bar into kPa? 1 bar equal 100 kPa. 一個 bar 等於100個 kPa. What is 1 kPa? 1 kPa is 1 kilonewton per square meter. Temperature, 25 degrees centigrade. Now, it is a must. Temperature of a perfect gas must be in absolute term. So therefore, how to change 25 degrees centigrade into absolute temperature? How? 25度 C 即係幾多啊
298 K.
Very good. Because the 25 plus 273, that gives you 298 K. Okay, so and then it is compressed to 6 bar. 6 bar again, change it into 600 kPa. So now P1 equal 100 kPa, T1 equal 298 K, P2 equal 600 kPa. The process is P times volume V to the power gamma equal constant, adiabatic, as line flow. So what we want is first find the final temperature, and then the heat and work of this compression process when the working fluid is of 1 kilogram per unit mass. Okay, so let us go to the solution then. 喺呢度對條題目有冇問題？OK， 第3條。第3條係 air T1 P1 100 kPa, T1 298 K, P2 600 kPa. It's going through an isentropic line flow process that is PV gamma equal constant. Now, based on that, the process characteristics is PV gamma equal constant, and the gas working fluid is a gas. Therefore, we always have two equations. We always have two equations to help us to solve the relation between the pressure ratio and the temperature ratio and the volume ratio. 記唔記得啊？我哋永遠都有兩條 equation 係幫到你嘅，永遠。只要係 line flow， 只要係 perfect gas， 咁咧就有兩條 equation 永遠都可以幫到你嘅。第一條就嚟自個 process 本身嘅 adiabatic process PV gamma equal constant. Perfect gas, PV over T equal constant. Now, based on 呢兩個 equation 啦，我哋可以 deduce 得到 pressure 同 temperature 之間嘅關係。That is T2 over T1 equal P2 over P1 to the power gamma plus 1 over gamma. Right? P2 over P1 is 6. 600 over 100 is 6. Gamma 1.4. For air, it is always 1.4 for air. And then T1 is 298. Based on that, we can work out T2. Any problem? And then we start to tackle the heat and work. Now, a diabatic process, you do not need to do any calculation, because a diabatic, this word already means that there's no heat transfer. No. So therefore, heat transfer is 0. Then we put it back into the law and flow equation. Q12 minus W12 equal to mass times U2 minus U1. Q is 0. M is 1. And then we can rewrite U2 minus U1 into CV times T2 minus T1. Right? Perfect gas, U equals CVT. Therefore, the work done is CV times T1 minus T2. Why? I changed from T2 minus T1 to T1 minus T2 because we have a negative sign. Before the W12. Okay? So therefore, take this negative sign to the right side and reverse the position. So I know T1, I know T2, I know CV. So therefore, I can work out what is the work done. And the work done is minus 143.04 kilojoule minus a direction. Means that the work is now applying from the surrounding into the system. Negative work. So, finish. Okay. So, any problem about that? Any problem? Please. 有問題？好啦嘛，冇咧，我哋就開始講第二樣啦。In that case, then let us change to the flow, a flow system. So now we change from non-flow to a flow. In front of you is a box, but this box we allow the working fluid to enter continuously from section 1, and then we also allow the working fluid to leave at section 2. So fluid is allowed to enter and also allowed to leave the system. Therefore, it is a typical flow system. And the process undertaken by the working fluid, that is, it enter from state 1, point 1, and then go through the system and then leave at point 2. between point 1 and point 2, then let us work on that. What we will do, again, is also carrying out an energy balance of the working fluid. The working fluid is flowing through the system with a certain mass flow rate m dot. M is mass. Put a dot on top of mass, that is the mass flow rate. In other words, mass per second. Kilogram per second, right? So we are talking about a flow rate. So therefore, on top of the mass, we have a dot, m dot, right? We are assuming that the mass flow rate is constant throughout. Therefore, we call it a steady flow. Then, in this box, the fluid will go through the box. And inside the box, we have some heating elements. We have a heater there, providing heat. Therefore, providing heat to heat up the fluid. And inside the box, we also have a rotor, such that the working fluid flowing through the rotor, drive the rotor, and then to produce a power output. Both Q and W have a dot on top. That means, talk about the heat is the rate of heat transfer, how many kilowatt of heat is supplying to. And for the work, it's the rate of work done. Therefore, it's the power, also in kilowatt. So the working fluid can go through and then absorb heat and then produce work. So therefore, we can add energy to the fluid by the heat. And the working fluid will also produce a power output through the rotor to the surrounding as power output. What other energies will have involved in this system? Then let us look at the inlet first. At the inlet, when the working fluid, assuming that a working fluid mass is now entering into the box, together with its mass, it will bring internal energy in. Fluid always have internal energy. However, for a flow system, we already explained that in order for the fluid to enter into the system, then the fluid need to produce a work, a displacement work on the previous fluid in order to push the fluid in such that it can replace the space left by the fluid mass, the other fluid mass. So therefore, usually for a flow system, for convenience, we will simply add the internal energy of the fluid mass together with this displacement work, and we call it the enthalpy. So therefore, in a flow system, instead of considering the internal energy, we will consider the enthalpy. And in fact, enthalpy is just a little bit more than internal energy. It's U plus PV. At the inlet, the working fluid enter at a higher position than the fluid leaving at the exit. This one is higher than the fluid at section 1. It's much higher than the fluid at section 2. Now, there is an energy associated with the position. The higher its position, then it will have a higher potential energy. So therefore, we usually draw a datum line. And then compare everything with the datum. So therefore, when related to the datum, the fluid ones will have a certain potential energy. What else? It is now, for example, it is now traveling with 20 meters per second into the system. Energy associated with the velocity, that is the kinetic energy. So related to its velocity, we have the kinetic energy. So therefore, at the entrance, there are three kinds of energy associated with the moving in of the fluid. That is the enthalpy H1. The potential energy related to its position Z1. Z1 is the vertical distance above the datum. And the energy associated with the velocity U1. Now, here, be careful. Here, in a steady flow system, I am using big U as the velocity, not internal energy. Right? So at the exit, we also have the enthalpy leaving with the fluid mass, H2. We also have the potential energy associated with its vertical depth, Z2. We also have the kinetic energy associated with the velocity, big U2. Three kinds of energy associated with the fluid mass in. Three kinds of energy associated with the energy of the fluid mass out. Join the balance. First, at the inlet, the three kinds of energy. First is associated with the fluid mass. It is the enthalpy. Associated with the velocity, that is the kinetic energy. Associated with its position, Z1, that is the potential energy. Enthalpy is the mass flow rate times H1. Kinetic energy is the mass flow rate times half of U1 square. Associated with the potential energy, that is the mass flow rate times G, that is the gravity, 9.81, times the height, Z1, above the datum. Three kinds. At the exit 2, also three kinds. And inside the system, we also have the energy transfer as rate of heat input and rate of work output. So inside here, we also have these two. Then we have energy input as Q, energy output as W dot. If there is a difference between these two, if there is an energy between these two, then this difference will be totally reflected by the difference between the total energy at the inlet compared with the total energy at the exit. So if we have energy more adding in, then total energy at the exit will be higher than the total energy at the inlet. But if we have a negative difference between the Q and W, then we need to take away from the fluid inlet. Therefore, the fluid inlet, the total energy must be higher than that of the outlet. So based on this energy balance, then we're saying that the energy input as heat and work. But be careful, always have a dot on top, because we are talking about per second. Will be equal to the mass flow rate times the difference between the enthalpy, the difference between the kinetic energy, and the difference between the potential energy. They must be equal in order to keep a constant energy level. Therefore, it gives us what we call the steady flow energy equation. Here, Q dot is the rate of heat transfer in kilowatt. W dot is the power or the rate of work done, also in kilowatt. M dot is the mass flow rate, kilogram per second. The first group, enthalpy, that is kilojoule per kilogram. Second group is the kinetic energy, so it's the U2 squared minus U1 squared divided by half. Here, U is velocity. The third group is the potential energy difference, so it's the G 9.81 times the height of the Z2 minus the height of the Z1. Again, please remember this steady flow energy equation. Please remember this steady flow energy equation. Okay? Now, this is a much longer equation than the non-flow. So therefore, it involves so many unknowns. Not just Q and W. In fact, so many unknowns. So therefore, you can imagine that solving of the steady flow will be more difficult. So in order to help us to use this equation, we normally rely on making some reasonable and good assumptions. Simplify the equation first. For example, in front of me, it is a boiler. So this flow system is a boiler. So now let us apply the steady flow energy equation to a boiler. A boiler involves no work. A boiler is purely just a box or a kettle, all right? So you use it to boil water or change it into steam. 等於你屋企個水煲一樣啫，大個啲咁解啫嘛。Therefore, normally a boiler does not have any work. 冇 work. And usually in a boiler, the potential energy difference between the inlet and the outlet are rather negligible. 好多時咧，出口同入口咧，會基本上喺埋同一個 level 嘅。就算唔係，咁咧計出嚟咧，嗰個數字都會好細嘅。所以咧，嗰個 potential energy 嘅 difference 好多時咧，我哋就唔計嘅咯。And then kinetic energy, again, in order to for the working fluid to absorb heat, therefore the working fluid got to pass through the boiler slowly. 行得好慢㗎，如果唔係咧，唔夠時間俾佢索熱㗎。So therefore, the difference between U1 and U2 is small. Therefore, kinetic energy are also usually assumed negligible. If W 0, potential energy negligible, kinetic energy negligible. So therefore, the static fluid energy equation become the rate of heat transfer is equal to the mass flow rate times the change of enthalpy between point 2 and point 1. Boom, that's it. 好簡單咯。Then what you need is to solve what is H1, what is H2. Then depending on what kind of working fluid it is, if the working fluid is a steam, then you are using the steam table to find H1 and H2. If the working fluid is a gas, then you change H into Cp times T, just as before, right? Second component normally is the turbine or compressor. In fact, in applying the static fluid energy equation, they are the same. They are almost the same. And in many situations, they are the same. For example, a compressor. Then we pass through a fluid in, apply a power, and then compress it up to high pressure. That is the compressor. Using the static fluid energy equation, compressor this time have no heat. We will not provide any heat in the compressor. So Q dot 0. Again, potential energy difference is normally 0 because we will usually arrange the inlet and the exit around the same level. Velocity. Sometimes you may have a difference in velocity. So therefore, it may not be always the case to cross out the kinetic energy. 未必㗎，視乎嗰條數點俾你啦。If we can cross it out, then make it very simple. The power is equal to the mass flow rate times H2 minus H1. So therefore, if the working fluid is a steam, then we can find H2 and H1 from the steam table. But if this is a gas, then we simply change the H into Cp times T, just as before. These are the two very simple cases. Now I'm talking about a little bit difficult case. This is a nozzle. A nozzle is a device making use of the change in flow area. So the flow area is keep on reducing, and then using this reducing in area, and then to increase the velocity. So the entrance of the nozzle is usually at a high pressure, but low velocity. And then we expect that the velocity will be increased to a very high velocity at the exit. But the steady flow energy equation still apply. Now, it also does not involve any work or heat. Low heat, low work. And potential energy change, no way. Because Z1 is usually equal to Z2. If it is the case, then the steady flow energy equation can be simplified to the change in velocity equal to the change in enthalpy. But here, be careful, because the right-hand side change in kinetic energy usually have the unit of joule. But on the left-hand side, the unit of the enthalpy usually kilojoule. So therefore, they are not equal in that case, because the left-hand side change of enthalpy is 1,000 times bigger than the right-hand side. So therefore, in applying the steady flow energy equation to a nozzle, this is something you need to pay attention to. Now, let us go to another problem solving. So this time, let's go to 5 and 6. Okay. So are you looking at the question that I'm showing you? 5 and 6?
Yes.
So first we talk about 5. A combustion gas. This is a gas. No doubt, a gas. At 5 bar and 500 degrees C, expand through a gas turbine to 1 bar. Now, a gas turbine, a flow process. So therefore, system, a flow system. Going through a flow process. Working food is a gas, combustion gas, giving you the Cp and the Cv. Cp is 1.2, Cv is 0.9. Right? And then it enters the turbine at 5 bar and 500 degrees C. So P1 is 5 bar, T1 is 500 degrees C. And then expand to 1 bar. The mass flow rate 0.1 kilogram per second. What I want to find is what is the temperature at the turbine exit, and also want to find the heat transfer and the power output of the turbine. Now, this is a gas. So therefore, pressure, we will use kPa, kilopascal. So 5 bar equal 500 kPa, and 1 bar equal 100 kPa. Okay? But for gas temperature, we should use absolute temperature. So don't keep it at 500 degrees C, but it should be 500 plus 273 gives you 773 K absolute temperature. Exit pressure 1 bar, so we change it into 100 kPa. In that case, let us make a start, right? Right. So therefore, it's a gas. P1 500 kPa, T1. Now again, don't keep 500 degrees C. Change it into 773 K. And P2 is 100 kPa. Steady flow. Therefore, a flow process. Therefore, we will use the steady flow energy equation. But first, we want to find the temperature at the exit first. Now, even though the relation between the pressure ratio and the temperature ratio of an isentropic process, that is T2 over T1 equal P2 over P1 to the power gamma minus 1 over gamma, we develop this in the non-flow process for a gas. But it can be used for a flow process. It can also be used for a flow process, except the work done, the heat transfer are not as predicted by the non-flow equation. But this temperature ratio and pressure ratio can still be applied. So therefore, we have found that the temperature ratio T2 over T1 equal to the pressure ratio P2 over P1 to the power gamma minus 1 over gamma. It can be applied. So T1 is 773. P2 over P1 is 1 over 5. And gamma, right, is 1.333 minus 1 divided by 1.333. So therefore, we work out the T2 easily. But for the work, then we need to apply the steady flow energy equation. So write out the steady flow energy equation. Q12 minus W12 equal m dot times the enthalpy change plus the kinetic energy change plus the potential energy change. Simplify. Low heat. Potential energy negligible. Kinetic energy negligible. So I cross out these three terms. Therefore, the power output is equal to m dot times h1 minus h2. And I change h1 into CPT1, change h2 into CPT2. Therefore, done. So therefore, what we got is 30.71 kilowatt, and it's positive That means a turbine is always producing a power to the surrounding, positive power. Right? Any problem? Any problem? Any problem?
阿 Sir 點解佢加碼又唔同咗嘅
？CP 係1.3，係咪啊？係1.2。CV 係0.9，呢個唔係 air 嚟喎，呢個唔係 air 嚟喎。我已經話呢個 combustion gas 啦，個 CP 1.2，個 CV 係0.9，所以加埋咧係1.2 over 0.9， 1.333。air 就一定係1.4啦。但係而家呢個唔係 air 啊嘛，係一個 combustion gas 啊嘛，條數話 ，O 唔 OK？
？OK， 唔該。
Right. So we go for another one. So we go for question 6. Now, steam and 2 megapascal and 280 degrees centigrade enter a nozzle with 20 meters per second. During the expansion, its specific enthalpy dropped to 2.89 megajoule per kilogram. What I want to find the velocity at the exit. Working fluid 係 steam， 所以咧，即係話呢條數咧，你千祈唔好再用 equation 啦，一定要用 steam table。Right? The system, a flow system, because it's talking about a nozzle. Fluid is entering a nozzle and leaving a nozzle continuously. Steam. Steam pressure. We should use bar. So therefore, 2 megapascal means 20 bar。一個 megapascal 係等於10個 bar， 所以兩個 megapascal 咧就係20個 bar。見到係 steam 嘅時候，永遠都黐住用 bar 做單位。OK？ Temperature 280 degrees centigrade. Now, steam, it is correct. We should always use degree centigrade for steam. For gas, then we should use kilopascal for pressure and absolute temperature K for temperature. But for steam, we use bar for pressure and then degree centigrade for temperature. And it enter with 20 meters per second. So it ends up with this velocity. At the exit, we're saying that the enthalpy is dropped to 2.89 megajoule per kilogram. Again, can we change it into kilojoule per kilogram? Certainly will be better because in the steam table, the unit for enthalpy is kilojoule per kilogram. So therefore, we can change it into 2890 kilojoule per kilogram. And then what I want is to find the exit velocity. 有冇問題？條數 If not, then we go to the solution. So are you looking at my solution? 你咪見到睇到 solution 啦。Okay. Okay.
Okay.
Steam. Now steam expand fluid also. So working fluid is steam, and the system also is a flow system. P1 change it into bar. So 2 megapascal equal to 20 bar. T1, it is good to remain as degree centigrade, 280 degrees centigrade. U1 velocity at the entrance is 20 meters per second, and the enthalpy at the exit is 2890 kilojoule per kilogram. So these are the given data. Now, steady flow. Therefore, we apply the steady flow energy equation. For LOSO, low work. A LOSO does not give you any work because the LOSO is a very simple device using changing the area to produce the velocity increase. So therefore, there's low work. Low heat, very small device, so therefore heat transfer is negligible. Potential energy change, negligible, because usually 1 and 2 are at the same level. So therefore, what we have is H2 minus H1 equal half U2 square minus U1 square. Right? Now, steam. We should use the steam table. Therefore, we go back to the steam table. Using the steam table, first, we need to identify what is this steam, or what is this H2O, a water, a wet steam, or a superheated steam. Therefore, the first thing to do is by comparison to identify what is each. So we go to 20 bar. So therefore, go to the table that is saturated water and saturated steam. Doesn't matter. Go to this table first. And then look at the saturation temperature, 212.4. That means at this pressure, the saturation temperature is 212.4 degrees centigrade. Now, if the given temperature is below this 212.4, that means you have a water. If the given temperature is above, higher than this temperature, then you have a superheat steam. If the temperature is exactly at 212.4, that means you have a, most likely, you have a wet steam, right? That means it can be something between the saturated water all the way to dry steam, because between these 2 points, the temperature is always equal to 212.4. Okay? So this time, high. So therefore, we know that we have a superheated steam. So go to superheated steam table. Pressure 20 bar. So therefore we read along this row. We have the reading at 250 degrees centigrade, and we have the reading at 300 degrees centigrade. But we do not have 280. So therefore, we need to work out the H at 280. How to work it out? By ratio, work it out. Still want to ask me how? Then write it down. It should be 3025. That is a H at 300. Minus 2904. This is the H at 250. Divided by 50. Multiple by 30. 乘返30 over 50. And then add it back to 2904. 咁咧，你就揾到200嘅時候嘅 H 啦。喺呢度，使唔使講多次？
好啊，好啊。
阿 Sir 可唔可以用中文講多次啊？
英文都聽唔掂咩 ？OK， 因為你要揾20個巴，280度 C， 咁你冇噶嘛？你係得250同300啊。咁於是乎咧 ，by ratio work out 翻佢。咁呢個20個巴280度 C 咧，個 value 咧就應該等於3025，呢個係300度 C 啦，減2904，呢個係250度 C 啦。將呢個數字3025減2904呢個數字咧乘30 over 50，因為300減250咧係50度啊嘛，但係280減250度咧就係30啊嘛，所以咪30 over 50咯。再將呢個數字加翻落去2904，咁 OK？O 唔 OK？
冇問題啊 ，Sir， 唔該你。
Okay. So therefore, now we found the enthalpy at 20 bar. Also at 250 to 280 degree centigrade. And I work it out, this 2976.6. 根據頭先條 formula 計出嚟咧，就係2976.6啦。H2 that is directly given to you is 2.89 megajoule, so it gives you 2890 kilojoule. H2, H1 are fine. It's 2976.6 minus 2890. And is equal to, the other side is half U2 square minus U1 square. U1 is 20, U2 unknown. But here got to be very careful because H is in kilo. H is in kilojoule. But the other side, kinetic energy, when you work it out, is in joule. The other side is in joule. So therefore, I need to multiply the enthalpy H by 1000. 乘翻1000，一邊係 kilo， 一邊唔係，相差咗1000倍，所以你要將個 enthalpy H 將佢化翻做 Joule 先，咁咧 ，therefore I can work out the velocity is 416.65 meter per second， 計到啦，400幾個 meter per second。Question? Any question? Okay. 有冇問題？ If not, then I hope you can go back home and then start to solve the problems at the end of this chapter. Right? Okay? So in that case, I see you. 點？
我想問係咪如果 steady flow 就冇個 level， 即係個 set 就係0。
邊個話？
即係如果 steady flow
係
個 set 就係0，即係個 level 就唔會有 level 嘅 difference。
唔係㗎，唔係㗎。Set 2 and set 1 is the potential energy, right? And also, this potential energy, when you work it out, is also in Joule. 9.81去乘 2Z2 減 2Z1， 2Z2 減 2Z1 有幾多啫？俾你1個 meter 嚟，好唔好啊？1個 meter 乘 9.81， 咪 9.81咯，係 Joule 嚟啫喎。前邊個 H 咧係 kilojoule 喎，1000倍喎。所以咧係計呢類數啦，我哋往往都第一時間啊畫咗嗰個 potential energy 㗎啦，佢唔係 exactly 等於0㗎，唔係一定等於0㗎，唔係㗎。但係就算唔係等於0啦，都係一個好細嘅 value。當你同個 enthalpy 比較咧，根本係冇得比嘅 ，right？
我明你意思，即
係佢唔係一定係absolute zero 㗎，佢可能係 negligible 嘅啫。譬如計出嚟係幫你個 H 比較啦，佢可能係你呢個 H 嘅1% 都冇，可能係0點幾個 percent， 計嚟做乜啫？係咪啊？咁咯。
I know what you mean.
Okay. So if not, then I will see you next week. 下個禮拜見你哋啦。OK。中間有乜問題嘅，可以俾 email 又俾我，好唔好 ？OK。
Okay, thank you.
拜拜。
Bye bye.
In that case, bye bye. Bye bye. See you next week.